Alright, let's go ahead and solve a problem based on the heat pump. We talked about the theory of a heat pump that can produce the cooling effect and the heating effect as well. So for this problem, particularly 11.44, it's for residential heat pump, and then it has all this operating condition. So based on this heat pump, let's just draw the TS diagram first and then also the pH diagram. So this would be the TS diagram. Okay, so in this TS diagram we know that ideal refrigeration cycle and also the actual refrigeration cycle. So the ideal refrigeration cycle would be something like this: 2, and then constant pressure line here, 1, 2, and then expansion valve, right, 3 to 4, and then 4 to 1, basically this. So this would be the actual ideal cycle. However, it says that one of the question in this problem is asking us the isentropic efficiency of the compressor. So isentropic efficiency of the compressor means that we need to have the comparison with the actual. So if it is the isentropic point or the ideal point, the actual would be something like this. So this would be 2a. This is the actual. Okay, so excuse me. So this is the TS diagram, right? Basically we know that the W in or the W compressor, and then this is the heat rejection QH, and then this is the heat addition QL, right? And this is the expansion valve 3 to 4. Anyway, so the pH diagram will look like this: pressure versus enthalpy. Okay, so that diagram, it's basically 1 to 2, 1, 2, 3, constant enthalpy 3 to 4, and then 4 to 1. Okay, so here it's WC, Q out, or the key high temperature, and Q low temperature. Okay, so that's our pH diagram and TS diagram. So now let's take a look at what are the conditions it's given. So we have to determine the compressor efficiency, and also we have to determine the how much heat supplied to the heated room. So heated room. So basically that QL or the QH, we have to determine this, right? All this information are given here. So for example, first we will start with this compressor, which is the point 1 to 2, right? So point 1 to 2, what is given for this particular problem, they're saying that the refrigerant enters the compressor at 200 kilopascal and superheated by 4 degree Celsius. Okay, so in this superheated refrigerant and also the pressure 200 kilopascal, we have to look at the table and get this respective data, right? So for example, state 1, what are the things we have given? For example, refrigerant is given. Refrigerant is 134A. Okay, this is the refrigerant, and then the temperature is given. It's 4 degree Celsius. It is 4 degrees Celsius, T1, and then also the pressure is given, P1, which is equals to 200 kilopascal. Okay, 200 kilopascal. Now from the table A13, which is the refrigerant, superheated refrigerant, we will get the enthalpy and entropy. So I copied all this information right here. So this is table A13, which is superheated refrigerant 134A. So in this table we'll look for the enthalpy and entropy based on the 200 kilopascal, which is 2 megapascal right here. Okay, 0.2 megapascal, and then 4 degrees Celsius. So if we basically if we do the interpolation in between 10 degrees C and 0 degrees C, then we'll get this enthalpy in between this line, and then entropy in between this line. Okay, so I have already done this interpolation. So basically at at point 1 H1 enthalpy would be 256.48 kilojoule per kg, and entropy would be 0.98214 kilojoule per kg Kelvin. Okay, so now from the TS diagram, what we know is that point 1 and point 2s is the same, right, for isentropic condition. So we don't know about the 2a, point 2a. So how can we calculate the point 2a at point 2? Okay, so at point 2, right, basically with respect to at point 2 we have this information right here, which is the inlet of the condenser, which is that it says that inlet of the condenser 800 kilopascal and 50°C. Okay, so now let's take a look at this pressure, 800 kilopascal. So at state 2 pressure 800 kilopascal and the temperature is 50°C, and then entropy, which is S2s equals to S1, which is we got from this one 0.98214. Okay, so with respect to this entropy and also with respect to this pressure, let's take a look what is the enthalpy, right? So the enthalpy H2s from this table, excuse me, let me write this table number, table A13, right? Table A13 will get H2s equals to 279.45 kilojoule per kg. So let me go ahead and show you. So this is table A13. Okay, in this table A13, pressure is 800 kilopascal, that means 0.8 megapascal, which is this table. Okay, and then the temperature or the temperature is 50°C. So this 50°C, this is actual enthalpy is this one and entropy is this one. However, the isentropic enthalpy isentropic enthalpy H2H will be depending on that that entropy. So we have the entropy, which is 0.98214. So excuse me, 0.98214 and 0.10, and this entropy we have to do the interpolation in between these two entropy, then we'll get another enthalpy. Okay, so that enthalpy would be H2s, and this enthalpy right here 286.71 is H2a. Okay, H2a, this is actual. However, H2s would be coming from the interpolation. Okay, so that's what we did here. So H2s, this is came from interpolation. Okay, basically S1 and the S1 and which is S1, which is basically 0.98214 and another entropy which is 1.0005. Okay, so if we do the interpolation of this one, then we'll get this H2. Okay, and then H2a, which is the actual enthalpy with respect to 50°C, it is 286.71 kilojoule per kg Kelvin. No, it's only kilojoule per kg. Okay, so now we know that H2a, H2s, right? So the part A, it's telling us what is the isentropic efficiency of the compressor. So the compressor isentropic efficiency, we know the formula H2s divided by H2s minus H1 divided by H2 minus H1. So basically if we plug in all this information, it will be, it has C H2s, we know that 279.45 minus H1 256.48 divided by which H2a, which is 286.71 minus 256.48. Okay, so the efficiency 279.45 minus 256.48 divided by 286.71 minus 256.48. So it would be 0.7598, so which is equals to 76%. Okay, the efficiency, compressor efficiency. Now for part 3, or for point 3, what we know? Point. So in this point 3, which is the condenser outlet, right here, point 3, it's the condenser outlet, right? So it says that when it's leaving the condenser, the pressure is 750 kilopascal and subcooled by 3 degrees Celsius. So basically this point, it's 750, it's when it's leaving the condenser, it's basically the pressure is decreasing to 750 kilopascal and subcooled by 3 degrees Celsius. This is a critical information right here. So in this point 3, we know that pressure P3 equals to 750 kilopascal. Okay, and also from the table 11, A11, which I copied right here, this is saturated refrigerant, right? So with respect to that pressure 750 kilopascal, so right here we have 720 and also we have 770. So we don't have 750. So if we take the interpolation of these two, then we'll get a temperature. Okay, saturated temperature right here. So saturated pressure and the saturated temperature. So from table 1, with respect to 750 kilopascal, the saturated temperature is equals to basically 29.047 degrees Celsius, and we got this by interpolation. Okay, interpolation. Now with respect, problem is telling us that it's subcooled by 3 degrees Celsius. So the temperature at point 3 would be T saturated minus T subcooled. Okay, so which is 29.047 minus subcooled is 3 degrees Celsius, which is 26.04 degree Celsius, right? 26 degree Celsius. So now we know that, excuse me, now we know the temperature at point 2 as well as the pressure at temperature at point 3 and pressure at point 3. Now we can get this from the same table 11, A11. We will get the H3, which is equals to 87.83 degree Celsius, right? Basically if you look at the table A11 here, right here, so with respect to 26 degrees Celsius, we know that enthalpy is 87.26. This one is no enthalpy HF right here, this line. Okay, .83. Okay, so that's what we wrote here, 87.83 kilojoule per kg. So now we know that H3, pretty much all of those point. Then the heat addition, or part 3, is basically asking us, part B is basically asking us what is the heating load, right? So the heating load is equals to mass flow times H3 minus H, in that case it would be H2 minus H2, because enthalpy of a point at 2 is high. So H2 minus H3, right? So mass flow, we know that it is 0.022 kg per second, right, times the H2 286.71 minus 87.8 3, so it would be 0.022 times 286.71 minus 87.83, 4.37 kilowatt. So that's the heating load, okay, or the heating effect. So that is the answer for number C. And then another part is basically asking us that we consider that actual and ideal, right? So and then part C is basically asking is that what is the coefficient of performance of that heat pump. So the COP of heat pump, part C, coefficient of performance of the heat pump is nothing but heating effect divided by the W, right? W in. So heating effect we got 4.37 kilowatt, right? And basically W in mass flow times the H2 minus H1, which is the compressor, right? So if we plug in all this information, 4.37 divided by 0.022 times H2, we got 286.71 minus H1 256 minus 48, right? So if you plug in all this information, it will become 4.37 divided by 286.71 minus 256.48. So it would be 6.5, right? Coefficient of performance would be 6.5. So kilowatt, and this is also kilowatt, so it would be unitless. COP of heat pump is 6.5. So that is the answer. And then last part, which is the part D, it is basically asking us that what if it is a ideal cycle, right? So what coefficient of performance and heat rate, basically QL, if the heat pump operated on an ideal vapor compression cycle. So if it is ideal vapor compression cycle, and then the cycle pressure limit is 200 and 800 kilopascal. So let's take a look on this problem how it will gonna look like. So if it is ideal refrigeration cycle, then the TS diagram would be look like this: 1 2 3 4, still it's the isentropic line, right? So it is asking us what is the QH, right, and what is the COP of this cycle. So basically for this one it's 200 kilopascal pressure line, and this is 800 kilopascal pressure line, okay? So with respect to this two, we have to determine what is the COP and what is the Q heating load, right? So it's the same problem. But we have to do it for ideal cycle. So at this point, what is the pressure? Point A, the pressure P1 equals to given 200 kilopascal, okay? So with respect to 200 kilopascal, we from the table A11, we know that H1 equals to 256.48. it's the same one, right? 48 degrees Celsius, and H2 equals to 0.98214 kilojoule per kg. And also we know that H2, we know that point H2s, right? H2 equals to, which is with respect to 800 kilopascal, we know that the enthalpy is 279.45 kilojoule per kg. So now the and also with respect to 800 kilopascal, we know that enthalpy at 0.3 and 0.3, which is the saturated liquid, so it will be table A11, right, not table A13 anymore. So this is for, excuse me, this is table A13. Okay, and then table A11, basically with respect to 800 kilopascal. Let's take a look. Right here, so if we do the, so it's 770 and 815, we have all this information. 700 and 750 right here, 93 and 96. If we do the interpolation, then we'll get at 800 kilopascal, right? So at 800 kilopascal, if we do the interpolation, it would be H3 equals to, where is that graph? It would be 91.24. No, it's not that. Okay. So this one is with respect to 770.64. We got the pressure, we got the enthalpy 93.58, and with respect to 815 .89, we got the pressure, enthalpy is 96.49. Then with respect to 800 kilopascal, the enthalpy would be 95.46. Yes, so it would be 95.46. okay, 95.46 kilojoule per kg. Okay, so now we know that H3. So basically pretty much we know everything. We should be able to determine the Q heating effect, right, which is mass flow times H2 minus, again, H2 minus H3, right, 0.022. H2 we know 279.45 minus 95.46. Okay, so the QH would be 0.22 times 279.45 minus 95.46, 4.04 kilowatt. And and the COP of heat pump would be QH divided by W compressor in, right, which is 4.04 times mass times H2 minus H1. So it would be 4.04 divided by 0.0022 times H2. We know that 279.45 minus H1, which is equals to 256.48. So if we solve this, COP of heat pump would be 0.04 divided by 0.022 times 279.45 minus 256.48, 13.18. So in ideal case, coefficient of performance is high compared to the actual case. We can see that coefficient of performance is 6.5, where in ideal case coefficient of performance is 13.18, right? So that's the difference between ideal and actual cycle, and that's all about this problem. So thanks for watching this video. We'll come back with a new topic and new problem.